Hello, 8th grade girls. We are going on to the next section in science today, which is screws, wedges, wheels, and axles, which is 4.3.4. Figured I'd use some Northern Lights background, which is probably better on the eye than my sewing/laundry room. So enjoy. I know it's a little fuzzy, but hopefully it's not too distracting. I think Sam the science cat wants to join us tonight. Maybe not. Okay, goodbye, Sam. All right, so we're moving on to the next simple machine, or a series of simple machines today, that allow work to be done in an easier manner. So we're going to dive into screws, wedges, wheels, and axles. Let's start with our objectives and our vocabulary. Objectives: describe the advantages for using different simple machines, and to calculate the mechanical advantage of screws, wedges, and wheels and axles. Some vocabulary. A screw is a simple machine that consists of an inclined plane wrapped around a cylinder. A wedge is a simple machine that consists of two back-to-back inclined planes. And a wheel and axle is a simple machine that consists of a wheel attached to an axle that has a smaller diameter. All right. The screw is a simple machine that consists of an inclined plane wrapped around a cylinder. Think of threads of a screw as a very long inclined plane. An inclined plane increases the distance but decreases the amount of force needed. When a screw turns, it moves a certain distance up or down with each rotation. The screw exerts effort force over a long distance. A jar lid is an example of a screw. It would be hard to seal a jar tightly by pushing down on the lid, so the jar lid is threaded. The effort force is small when the lid is turned, but it is multiplied because it exerts over a long distance with each turn of the lid. The pitch of a screw spans the distance between two adjacent threads along the length of the screw. This measures the depth that the screw will advance in one complete rotation. The closer together the threads sit along the screw, the longer the distance over which the effort force is exerted, and the more the force is multiplied. Screws with threads that are closer together then have a greater mechanical advantage than screws with threads that are farther apart. They also have more holding power. So if you have seen a screw before, screws come in all shapes and sizes. I know it's a little fuzzy. So here's an example of a screw. And so screws have different tops. This one has a Phillips top. We have one that looks like this on the top. Okay, a little different. And we have one that looks like this on the top. So an inclined plane, so over a cylinder, so your screw is shaped like a cylinder. It's circular and it has at least one flat end. The other end is a point. But along the cylinder, you have the threads, which are these little lines that go up or down your screw. And the pitch is the distance between each thread. Okay, so if I bring this closer, so you have from here to here, this first section is the pitch. Okay, so you have many pitches all the way down your screw. So the distance, or how wide your pitch is, determines the mechanical advantage. How long it takes for one rotation to go all the way to go downward. Okay, so the closer your threads are together, the greater the mechanical advantage. It's going to take a longer time to get it in, but the effort force that you have to exert is less because of the closer distance together. And so as you're screwing it down, it is going to take a longer time, but it'll be easier to get that screw in than if you had a screw that had a much bigger pitch. So these look sort of similar. This one has bigger pitch than the other one. And so to screw this in is going to take more effort than it does to screw this in, because you are making up the distance between these two pitches, or between the pitch with your own effort rather than the effort of the inclined plane. Okay, now the mechanical advantage of a screw, so MA for mechanical advantage, like we talked about the other day, is determined by the circumference of the head. So the head of your screw is the top, which is always circular, okay? So the circumference of the head, whew, I lost myself. Where'd I go? Let's see. All right, we'll do it like that because that was a little creepy. Okay, we're gonna continue like this. So the head of your screw, okay? So the circumference of the head of your screw divided by the pitch. So how tall the pitch is. Now, if the circumference equals pi, that little symbol is pi, 3.14, times the diameter, okay? So that's circumference of a circle, pi times the diameter of a circle. So the diameter of your head of your screw, okay, will allow you to find the circumference of the head of your screw. Once you know the circumference of the head of your screw, then you figure out what the pitch is. So if a screw head had a diameter of 0.4 centimeters, multiply that by pi to find the circumference, 1.25 centimeters. If the pitch is 0.1 centimeter, then the mechanical advantage would be 1.25 centimeters divided by 0.1 centimeters. And you would end up with a mechanical advantage of 12.5. So the formula you're using for that is the screw's mechanical advantage equals the screw head circumference divided by the pitch of the threads. Okay, so the distance around your screw head divided by the distance between the threads. And you can see a picture of that on the next page. There's a picture of a screw and it gives you the formula. Now, it may seem that a mechanical advantage of 12.5 is very beneficial, but experience says that fingers do not have the strength to turn screws with bare hands. If you've ever tried that, trying to screw a screw into a piece of wood with your hands, you might get it in a little bit, but after a couple turns, it's not going anywhere. You need another simple machine to allow you to get that screw all the way into the wood. A screwdriver is needed to increase the strength. Using a screwdriver increases the diameter because the handle's diameter is larger than that of the screw head. Consider the mechanical advantage of the screw noted earlier. Suppose it is turned by a screwdriver that has a handle with a 3 centimeter diameter. Find the circumference, so 3.14 times 3 centimeters, the diameter, equals 9.4 centimeters circumference. Now we're going to take that circumference and divide it by the pitch of 0.1 centimeters to get the mechanical advantage of using a screwdriver with a screw. So 9.4 centimeters divided by 0.1 centimeter is 94. So now that is a mechanical advantage. So trying to do it with your hand, you would only have a mechanical advantage of 12.5. Adding a screwdriver to it, now your mechanical advantage jumps to 94. And so that helps a lot. So here's my screwdriver. Okay, here's my screw. If this is the circumference of the head of my screw, the circumference of the head of my screwdriver is obviously a lot bigger. And so that's going to allow more mechanical advantage. And so rather than trying to hand screw a screw into a piece of wood, when you use a screwdriver, this actually has a different tie. So all right. So when you attach that screwdriver in, they have the same tips. Okay, so the screwdriver fits perfectly in, and then as you turn the screwdriver to get that screw in, you're going to have a much easier time of getting that screw into whatever you're screwing into, wood, the wall, than if you were trying to do it by hand, because your screwdriver increases your mechanical advantage due to the fact that the circumference of the head of your screwdriver is larger. And then if you think of an electric screwdriver, or if you were to use a drill, okay, that has an even larger circumference and you're using an engine power. And so that's going to get that screw into the wood in a fraction of the time that it would take for you to use a screwdriver. All right, let's go on to the next simple machine, the wedge. A wedge consists of two back-to-back inclined planes. Remember, an inclined plane is like a triangle. You have a horizontal line and then a gradual increase in the angle of the plane. Okay, so a gradual increase is an inclined plane. So this is two inclined planes put together. Instead of the force being magnified by pushing an object along a slope, the wedge actually separates an object or pushes it apart. The greater the distance a wedge moves, the greater force it applies, which then produces a greater mechanical advantage. Imagine splitting a log with an axe. What shape of an axe head would be best for splitting a log? A long, thin wedge would take much less effort than a short, thick one. Now, this is one thing I've been doing during quarantine that I love, is splitting wood. We have a ton of wood that our friend who owns a tree cutting company had given us. We have a wood stove, so we burn a lot of wood. And so every couple of days I'll go outside and I will split wood with an axe because I love it. It's so fun and it's so rewarding, and it's great. So I usually use a much bigger axe, but this is a smaller axe. This is kind of like a hatchet that's used to break smaller pieces of wood. But on an axe, you have a sharp point at the end. You can see how thin that is, okay? But you have two inclined planes. So if you think of this being the center point and you have your plane is inclining this way, and the other one is inclining this way. So it's forming a triangle. It tapers down into a single point or a line, and then on the other end, it's a lot thicker. And so you can see, if we look this way, that from the starting point, from like your vertex, if you're thinking of an angle, you are increasing the inclined plane in both directions. So if you drew a line right down the center here, it would be like you had two inclined planes put together. That forms a wedge. A wedge, you have a larger end and you have a pointed end. Now, if I were to take, I'm going to put the camera back on just in case. If I were to try and split a piece of wood with the flat end, I might put some dents in it, or if it was a really dead piece of wood, it might crack, but that's not going to really do anything good for me if I'm trying to split a piece of wood in half or into pieces. So I could bang it all I wanted with this end, this flat end, and nothing would happen. But with an axe, when you have that short, sharp, thin line that is going to make a cut into the piece of wood, and then the wedge provides separation. So as that axe goes into the wood, it cuts the surface, and the more force you have that pushes it into the wood, that wood is then forced apart because of the wedge. And so when you have a very thin, longer axe, it's going to do a lot more than if you had a short, wider axe. We have two axes, large axes, and one is very thin and it's 4 pounds, and the other one is pretty thick. It has a tip on it, but it's pretty blunt, and a lot wider, and that's like a 8 pound. And so it weighs more, and you would think, oh, an axe that weighs more is going to have more mechanical advantage because it's heavier and it's going to just smash that wood into pieces. Not necessarily. Most of the time I use the 4 pound axe that's thinner and a little longer, because what it does is it allows it to break the surface of that piece of wood, and even the slightest wedge sometimes is all it needs for it to pop apart. If you have a pretty wide end, then the chances of it breaking the surface are pretty slim. And so you would use a wider wedge once you already have a crack, or you already have a beginning point. And so that wedge will help to really break apart something that's firm and really solid. But when you're starting, you want to start with a longer, thinner wedge to break the surface. And then that wedge is going to split those pieces apart. And I'm telling you, Cutting wood is not always a one whack and you break it apart. Usually you have to hit it and hit it and hit it and have good accuracy to hit the same spot over and over again, but it's a lot of fun. I love it. So wedges are really handy when it comes to wanting to split something apart. So it said, unlike we were talking about before, pushing something up an inclined plane, instead of pushing force up an inclined plane and the inclined plane allowing that to become an easier job, now you're using an inclined plane, two inclined planes, to separate things, to break them apart. Okay. Knives, chisels, plows, and axe heads are all examples of wedges. Tremendous force is exerted on the wedge as well as whatever material is being pushed into or through. Although the efficiency of wedges is low because their friction is so high, they are very efficient at converting a large impulse force into a large force perpendicular to the direction of the moving wedge. The advantage of a wedge is more about changing the direction of the force than magnifying it. The mechanical advantage of a wedge is calculated by dividing the length of its slope by its height. Okay, so the length of its slope by the height that you are dropping it from. So if you go back to the page before, it shows an example of what this looks like. So you have the height of your wedge. Okay, if you look at your page here, you have the height of your wedge, so that would be the height of the end of the axe compared to the length, how long that blade is. Okay, so the height here compared to the length. That is how you would find the mechanical advantage of a wedge. All right. And just going back to what they were saying to give a little bit more explanation about the lines perpendicular and what they were actually talking about. When it says that they are very effective at converting a large impulsive force into a large force perpendicular to the direction of the movement. So if you have your axe and you have a large force that you're hitting down, the piece of wood that you're hitting, I have a safety on this, so don't worry, it's not going to cut me. If you are coming down, this piece of wood is perpendicular to what you are hitting. Okay, so perpendicular means that they cross, okay, or makes like a T. All right, so if your axe is coming down, that piece of wood is now perpendicular to your axe head. And so you have force being brought down to a force of gravity that's sitting there, perpendicular to it, and it's allowing it to break it apart. Okay, that's what that's saying. All right, so we have screws, we have wedges. Now we're going on to axles and wheels. The wheel and axle is the most common simple machine used to transfer motion and force from one place to another. A wheel and axle is made of two circular pieces, a wheel or disc attached to an axle or shaft. The wheel is always have a larger diameter than the axle. The wheel and axle are firmly attached to each other, and when one moves, so does the other. So I just happen to have a wheel and an axle here. And so you, like it said, your wheel or your disc has a much larger diameter than that of your axle. Okay, this has a quite small diameter in compared to the diameter of your wheel. Okay, and as the axle moves, the wheel moves. Axles are usually attached to an engine, motor of some kind that moves gears along to move that axle, which then moves the wheel. Okay, and so the creation of the wheel obviously was one of man's prize inventions because it allowed for all work to be done much easier. If you think of from carts pulling things along to mills that were run by windmills that could grind corn. So you have mill wheels of stone that turn and grind things. So the wheel has been used in so many different facets over history and has allowed for work to be done in a much easier way. All right. Screwdrivers, wrenches, steering wheels, and doorknobs are all examples of wheels and axles. So when we think of wheels and axles, you might think of a car or a bike or a cart, but it's a lot more than that. So screwdrivers we talked about before, okay, is you're moving along an axis. If this is like your axle and you are moving this wheel, it's all moving in the same direction, okay? Same thing with a doorknob. When you turn the doorknob, the shaft that it's attached to turns in the same direction at the same speed to then open a door. All of these are considered wheels and axles. A wheel and axle work easier by magnifying the force that can be exerted on something. But like other machines, a wheel and axle does not change the amount of work that has to be done. If the force decreases, the distance over which the work is done must increase. In the wheel and axle, the wheel always moves over a greater distance than the axle because the wheel is larger. The force applied to the wheel is multiplied when it transfers to the axle because the axle travels a shorter distance. If the radius of the wheel is 6 times greater than the radius of the axis, the force exerted on the wheel is multiplied by 6. So like we said, the radius of your wheel from your center point to the edge is a lot greater than the radius of your axle from the center point to the edge. And so the wheel has to turn a lot more to go the same distance as the axle, one rotation. Okay, if you think of it like running track, if you are on the inside of the track, you really have a shorter distance than if you're running on the outside of the track to go the same distance, okay? All right. So when it comes to the size difference of your axle, so let's say it said if your diameter of your wheel is 6 times larger than the radius of your axle, then it's magnified by 6. So the force exerted on the wheel is multiplied by 6. They're in correlation with each other. The mechanical advantage of a wheel and axle is calculated as follows. Wheel and axle's mechanical advantage equals the wheel's diameter divided by the axis diameter. If the wheel's diameter is 25 centimeters and the axle's diameter is 5 centimeters, then your formula is going to look like mechanical advantage equals 25 centimeters divided by 5 centimeters. And so 5 is going to be the mechanical advantage of that wheel and axle. Applying the effort to the wheel magnifies the force on the axle 5 times. Consider the steering wheel of a car versus that of a large truck. The car is not as heavy, so the steering wheel is not as big. A semi-truck has a very large steering wheel because a great amount of force is needed to move the tires. A larger steering wheel gives greater force. The trade-off is the distance the wheel must be turned. The steering wheel must be turned a greater distance around to provide the greater force. So if you think of the steering wheel of, let's say, a go-kart, which is about this big, you can turn that whole thing around pretty quickly because the wheels are a lot smaller and you can turn them a lot easier. There's less friction on the road because they're a lot smaller. And then you think of a school bus or a semi-truck, usually they have steering wheels about this big, and sometimes they're even flat instead of up in front of you, so they can be turned this way because they're so large. So in order to move those really large tires, you have to have a bigger steering wheel, but with that comes a bigger distance. So your little go-kart steering wheel, your distance is this, whereas your steering wheel for a semi-truck moving much larger wheels, you have a much larger distance to turn those wheels. Another thing would be a schooner or sailing ships that have a steering wheel on them. So some run by an engine and a rudder now, but if you think of schooners like the Adventurer or the Lannon that we have in town, they're run by a steering wheel. And so that steering wheel moves the rudder to allow the boat to move. And so the larger the ship, the larger the steering wheel. So if you've been on a small sailing ship, or seen a small sailing ship, one person can man that steering wheel. It's usually a wheel with handles on it so you can grab them as you turn it, and it's manageable with one person. My brother's in the Coast Guard, and he is stationed on the Coast Guard's large schooner ship called the Eagle, which is massive. And so for their steering wheel, they actually have, I think it's 3 steering wheels all together, one right after the other. They're all kind of sandwiched together, and the steering wheel is taller than I am from ground to top. And so it takes multiple people to turn these steering wheels, and the steering wheel about this big needed to turn a boat of that size. It's almost the size of a cruise ship. It's massive. And so the larger the boat, the larger the steering wheel that is needed. Same thing with cars, same thing with anything that uses a wheel and axle. All right. Some other devices use the wheel and axle in the opposite way. On a fan, for example, the effort is exerted around the axle instead of the wheel. The force is reduced as it is transferred to the wheel, the blades, which has a larger diameter. At the same time, the distance becomes greater. The force travels at a greater distance, allowing the blades to travel farther and faster. A wheel and axle is similar to a lever. Apply force to the wheel, and the force is magnified in the same way the force is boosted in a first or second class lever. The force is applied to the axle. It is similar to a third class lever because the more force is required to achieve a greater speed. A wheel and axle can be used to transfer rotary motion to rotary motion, or to transfer rotary motion to linear motion. What does this mean? For example, a crank uses a rotary motion to raise and lower a bucket from a well. So if you think of a well, let me get a whiteboard here. Okay, so if you have a well, here's our wishing well. Okay, and it's made out of stone. All right, here's our well. Okay, in a well, an old-fashioned well, in order to get water, this is our ground. You have groundwater below, and you have a pulley here and a bucket that goes all the way down to the groundwater, and that's how you pull it up. And so you would use the pulley to pull that bucket back up. So a crank, if you had a pulley here, if you had a handle on this that you could just turn around and around and around, a crank to pull that bucket up out of the water. A crank uses a rotary motion to raise and lower a bucket from a well. The crank turns around and around as the rope and bucket travel in a straight or linear motion. So that bucket is going straight up or straight down, depending on what direction you are cranking the gear in order to pull it up. And so on this, the axle would be in the middle, and this obviously is the wheel. It's not on a long distance like a car where you have an axle with a wheel and a wheel. In this case, you have the axle and the wheel are kind of one piece, usually attached to the ceiling. And so it's a much shorter distance, but you have to crank it a lot more in order to get that bucket all the way up. All right. On the bottom there, there's a little chart that says gear ratios. Bicycle gears are often named by the number of teeth they have. So if you think of a bicycle gear, it has like spikes around the edge that holds on to the chain. Those are called the teeth, okay? A chain ring is the teethed ring that pulls the chain around the wheel. Standard size chain rings range from size in 36 teeth to 53 teeth. The rear wheel gears range from 10 teeth to 36 teeth. The ratio indicates how many times the rear wheel turns for every one revolution of the chain ring. Okay, so you can see in the picture below, you have ones that have more teeth at the top, so the black circle is larger, and then it gets smaller and smaller. So in that chart there, if your wheel ring has 12 teeth, your chain ring, if your chain ring has 53 teeth, then you're going to have 4.42. If your chain ring has 39 teeth, then you're going to have a mechanical advantage of 3.25. So you can see how the mechanical advantage increases with the increase of teeth. The less teeth there are on the gear, the less mechanical advantage you're going to have. Okay? All right, let's answer some questions together. So in the lesson review, you can do this on a lined piece of paper. Number 1, explain how the following simple machines make work easier. The screw, the wedge, the wheel, and the axle. And you can give examples of that. How does a screw make work easier? So if you think of, let's say, a nail compared to a screw, okay, a nail, you're just hitting it straight down in with a hammer, which is also a simple machine. But how is a screw, how does that make work easier than a hammer and a nail? And is a screw a stronger hold than a nail? Think about that. How about a wedge? Think about the different examples they gave of wedges, and how does that make the work that it does easier than it would have been without it? And a wheel and axle. How does that make life easier as well? Number 2, why is it that screws with threads that are closer together have a greater mechanical advantage than those with threads that are farther apart? Which would give a greater mechanical advantage? A screwdriver with a wide handle or a screwdriver with a longer shaft? So think about the formula for mechanical advantage of a screw. Was it the length of the shaft that made the difference? So the length of your screw shaft or the length of your screwdriver shaft? Was it that mattered? Or was it the circumference of the circle that mattered in the determination of the mechanical advantage? Okay? And with the pitch of your screws, why is it a greater mechanical advantage? Why is it that screws with closer together threads have a greater mechanical advantage? Remember, your threads are like an inclined plane going all the way up your cylinder, and the greater the inclined plane, the greater the distance that you have to go to get up the same distance in height, the greater your mechanical advantage is. Okay? So think on that. Number 3, find the mechanical advantage of a screw with a pitch of 3 millimeters and a head with a diameter of 8 millimeters. So let's go ahead and try this together. Let me get my whiteboard again. Okay. So if we have a screw with a pitch of 33 millimeters, so if this is our screw, our pitch between two threads is 33 millimeters. Okay? So 33 millimeters, and the head with a diameter of 8 millimeters. So that means the distance from here to here would be 8 millimeters. Okay, and so first we have to find out what the circumference of the head of our screw is. And so for circumference equals pi, which is 3.14, times our diameter. Okay, so we have 3.14 times 8, and when we multiply those out, 8 times 4 is 32. 8 times 1 plus 3 more is 11. 8 times 3 is 24, plus 1 more is 25, and move your decimal 2 places over. So we get 25.12 for our circumference. All right. Now that we have the circumference, now we can find the mechanical advantage. And so we can remember that the mechanical advantage of a screw head is diameter divided by the pitch, okay? And so we just found the circumference of our circle, and so we are going to do 25.12 divided by our 3 millimeter pitch, okay? All right, and so when we divide those out, we did 3 goes into 25.12, 0.12. We are going to say 3 goes into 25 how many times? 8, which is 24. We get 1. Bring down the 1. 3 goes into 11 how many times? 3 times, which is 9. I'm going to run out of space. 11, take away 9 is 2. I'm going to bring it up here. We're going to bring down our 2. 3 goes into 22 7 times, which is 21, which leaves us with 1. And so we have, we can add a 0 and bring it down. 3 goes into 10 3 times, which is 9. And we get 1, and we're going to get a repeating number there. Okay? And so our mechanical advantage, we could round that up from 8.373 to 8.4. So our mechanical advantage is going to be 8.4 millimeters, or just 8.4. We don't need to label it in units. Okay. All right, so hopefully that made sense to you, that the mechanical advantage is the screw head's diameter divided by the pitch. Okay, so let's go back and look at that for 1 minute. Oh, that's what's wrong. It's the screw head's diameter divided by the pitch. I was going to say, we just did circumference. Why isn't it circumference? So mechanical advantage equals circumference divided by the pitch. So that's going to be the mechanical advantage of a screw. Circumference, not diameter. We have the diameter. We use that to find the circumference. So circumference divided by the pitch of the screw. And remember, the pitch is the distance between the threads. All right. Number 4, what is the mechanical advantage of a wheel and axle with a wheel diameter of 300 centimeters and an axle diameter of 15 centimeters? So again, for our mechanical advantage of a wheel and axle, we can remember that that is the diameter of the wheel divided by the diameter of the axle. So we could say wheel diameter, so we'll do WD, divided by axle diameter. Okay, so if our wheel diameter is 300 centimeters and our axle diameter is 15 centimeters, 15 goes into 30 2 times, which is 30, and 15 goes into 0 0 times, and we have no remainder. And so our mechanical advantage is going to be 20. Number 5, how is a wheel and axle like a lever? So go back and read that section. How is a wheel and axle like a lever? And what we find with that is the advantage changes depending on where the force is applied. When the force is applied to the wheel, it's like a first or second class lever. So if the force is applied on the outside, the wheel, then it's like a first or second class lever. Remember, a first class level had 1 string or 1 rope that was being used. A second class lever had 2. Okay, and then when the force is applied to the axle, it's like a third class lever. All right, and if we go back and look at levers, I was thinking of pulleys for a minute. I meant levers. If we go back to look at levers, levers were all the way back on page 251. You have a picture there on 252 of a first class lever, which means that your output force is at one end and your input force is at the other end, and your fulcrum is not in the center, okay, the point where it pivots. That would be a first class lever. Second class lever, you have the fulcrum at the end, then you have your output force, and then your input force. And then your third class lever, you have your fulcrum at the end, and you're lifting the output at the other end. Okay, and so go back and look at those pictures and then picture that how it would work with a wheel and axle as well. All right, excuse me. Number 6, what is the mechanical advantage of a wedge with a slope of 400 millimeters and a height of 20 centimeters? And so we can remember that, let me just clear. Okay, we can remember that the mechanical advantage of a wedge equals the length of the slope. So the length of slope, okay, we'll do L of S, the length of slope divided by the height. Okay, now we also need to do a conversion here. So we have 400 millimeters, 400 millimeters for our slope, and we have 20 centimeters for our height. And so we need to end up with the same units. And so we are going to convert our 400 millimeters to 40 centimeters. They mean the exact same thing. Okay, we're just converting it to similar units. So now we have 40 centimeters and we have 20 centimeters. So if we were to do 40 centimeters, which is the length of the slope, divided by the height, which is 20 centimeters, 40 divided by 20 is 2. And so our mechanical advantage of this wedge is going to be 2. All right. That is all we're going to be doing today. We are not doing the lab for today. The next time we come together, we're going to talk about compound machines, which means machines that use more than one simple machine in order to get their job done. So they will have a combination of some of the simple machines that we've learned about, whether it's levers or pulleys, wheels, axles, wedges, or screws. You're going to see more than one simple machine working together in order to create an easier job. And those are called compound machines. So we will talk about that next time, and I hope you have a great rest of your day. Thank you, girls.